Hi, my name is Jingnan, and in this video, I'm going to introduce our work on optimum and robust category level perception from 2D and 3D semantic key points. This is joint work with Heng and Luca Carlone at MIT Spark Lab. In this work, we consider a category level perception problem. How can we reconstruct the 3D poses and shapes of a category of objects despite intra-class shape variability? More specifically, we employ an active shape model where for an object category we are given potential CAD models describing objects in that category. Each individual shape is then generated from a convex combination of the basis shapes. Based on this model, we then adopt a standard formulation where pose and shape are estimated from 2D or 3D key points. Such inputs may be the output of some neural networks and may contain outliers. Here are the two pipelines proposed in our paper. Top and bottom rows indicate our pipeline for 3D and 2D sensor data respectively. Our main contribution lies in the boxed area, specifically a category-level graph-theoretic outlier rejection layer called Robin, and robust and certifiable solvers for both 2D and 3D problems. Our first contribution in the paper is that we developed two certifiably optimum solvers, named PACE3D star and PACE2D star for 3D and 2D category-level perception problems. The standard formulations we use, while being expressive, are difficult nonlinear optimization problems to solve. For our solvers, we rely on the designs of exact semi-definite relaxation instead to achieve certifiability and optimality. Our second contribution is a robustness layer to handle outliers. First, we develop Robin, our graph-theoretic framework that rejects outliers by selecting the maximum hyperclick in a compatibility hypergraph. These hypergraphs describe compatibility between measurements and are built from using compatibility tests. We develop compatibility tests for both 2D and 3D cases. For the 3D case, we exploit convex holes formed by the same key point across shapes to check compatibility. For the 2D case, we are inspired by the concept of winding orders from computer graphics, which are simply clockwise or counterclockwise orientations formed by 3 points. By learning all triplets possible orientations, we can formulate a test that rejects triplets if their observed orientation is impossible. Let's look at an example. Consider 0, 1, 8. Due to their arrangement, it is possible to view them in both clockwise and counterclockwise orientation. Consider then these 3 key points. Due to occlusion, they can only be viewed in a counterclockwise orientation. By enumerating over all triplets, we can formulate a test that rejects triplets if their observed orientation is impossible. To further increase robustness, we apply a graduated non-convexity scheme to the solver based on earlier works from our lab. We call the resulting approach PACE2D sharp and PACE3D sharp. Here we show qualitative results of our methods, PACE2D sharp and PACE3D sharp comparing with other baselines. Here are some qualitative results of our proposed methods on the ApolloScape self-driving dataset. Thank you for your attention, and please refer to the paper for more details.